One last little subsection I want to talk about in this very first part of the unit is how we can get new graphs from old. And the idea here, there's actually three different things I want to talk about. One is to play off the idea of subset, really, to talk about what a subgraph is. So the formal definition looks as follows, and I'll give you a quick example of it. A graph H is a subgraph of another graph G if the vertices in H are vertices of G and the edges of H are edges of G. In other words, what we're doing is we're taking a part of G and that will be a subgraph if it's a part of G, pieces of G, and is a graph in its own right. So a key word here that may not stand out on first reading is that H has to be a graph for it to be called a subgraph. So let me just draw a graph or two and show you a subgraph. So let's take this one here. Maybe have this as our graph. G. I'll do one little more part here like so. So this is of order 1, 2, 3, 4, 5, 6. So that's G, and here's a subgraph, H subgraph. So I don't have to use all of the pieces there. So maybe I will leave out this vertex here and some other stuff. But if I leave out that vertex, I have to leave out those edges as well, right, in order for H to be a graph. So maybe I'll take this one here and that one there, like so. And I'll take this one here and maybe this one here like so. So there's a subgraph. Okay. Now here's another subgraph, another one. So this is H, say H2. So I'll take that part of G, that's this part over here. And I'll take the opposite corner there. And I'll take the middle piece right there. So I've taken these pieces right here. That's a subgraph, okay? It is a graph. It has order 6, like the original one, and it has edges that connect some of them. So it satisfies all the properties of graph. Every edge in a graph has to have two vertices, or that is, its endpoints must be in the graph, even if it's a loop, right? And these satisfy that. So those are two different ones that are subgraphs of that right there. A union of two graphs is really just what it sounds like. You put two graphs together. Technically, a union of graph G1 with the vertex and edge set listed, and G2 likewise, is a graph whose vertex set is the union of the two vertex sets. Put them together, join them, and edge set in like fashion. You join the two edge sets. You can include all the edges. That's what that means. Include all the edges. So let's draw a couple of them here. So let's say this is G1, and I'm going to label the edges because sometimes the vertices are going to be the same. So that's G1. And G2 will look like maybe this right here. So we'll have maybe 5 in this one. So here's A, B, and then it has F and H and J. Those are its vertices. And its edges maybe connect A to H and J to F, and I think I won't connect A and B in that one. So there's G1 and G2, and you just take the union of them. And I think a natural way to take the union of them, if you look at it right here, is to say to take this edge right here, that has to join those two. That's A and B. So that edge that joins A and B will be added on here, and then the C I'll stick off on the outside there. So the union would look like this. See if I can capture that same sort of orientation there. Looks roughly like that, where there's H, F, and J, and that goes across to A, and B comes over here like so. It's a little different scale. So now I've included the pieces from both graphs together. But the point is that if you have common vertices, those are treated as common vertices like so. Okay. All right. The complement of a graph, the last one we'll talk about in this video clip here. Complement here means whatever would is left out that would make the whole. So just like complementary angles in geometry, the two together would make a right angle. They complement one another in that sense. So the complement of a simple graph, and we'll just do this for simple graphs here. So I'll try to be real clear when we're just limiting it to a simple graph. On n vertices is a graph that we'll denote by putting a bar over it for complement here. On the very same n vertices, such that for each pair of vertices, UV is an edge in the complement if and only if it's not an edge in G. So what we're doing is we're deleting the edges in G and adding those things that weren't edges in G. So for example, we'll do this on 5. We'll take a graph here, G, on n vertices, like so. And I think what I'll do, whoops, I'll try to draw a straight line. Straight line. We'll take a figure A, close it off on the bottom like so. So that's G, and its complement would look like, well, for the complement, what I'm going to do is take the edges that I didn't include here. So 1, 2, 3, 4. I didn't include that edge, and I didn't include that edge, right? So I think that's all of them there. So the complement would have the same vertices, like so, and the edges that were not in the original graph. So all those outside edges weren't, and then these two cross edges here were not. That other cross edge was, and the bottom edge was there. Those cross edges were in there. So these are that, when I'm speaking of these cross edges, I'm talking about those. Those are not in there now. Okay, whoops, deleted that. So there's G complement. So an interesting thing about that, to close this out, is that of course these will not overlap in edges, but they do have all the vertices. So notice that if we take the union of those two graphs, what do you get? Well, you get all the edges on n vertices, so that will always be Kn, like so. Okay, that's a good way to think about it. They're both subgraphs of Kn. All right, we'll stop this one here.